Hi everybody, welcome back to class. What we're going to be doing today is continuing our lesson starting into the physical science topics. And this is where we start to hit the first true physical science topic. And with that, we're going to be talking about matter. If I could get this to work. So we're talking about matter. Now matter traditionally, at least here on Earth, comes in three different states. These are the most common: solids, liquids, gases. A Bose-Einstein condensate, which is this here, you will not typically see, so we're not even going to talk about that one. The other one here, the fourth state, is called plasma. With plasma, you can think about that with like lightning. When you see lightning, that would be plasma. And plasma, we'll talk about later this year, possibly a little bit, but that has to deal with ions and superheated gases. Now, when I talk about matter in class, typically when people, or anytime, people think about all the stuff. And again, stuff is what they think of in quotations here. And it's all the stuff that exists in the universe, or people will sometimes say everything is made out of matter. And it's not entirely true. And you got to be very careful how you say that. In this class, in science, and in any science, matter is anything that has to have both mass and volume. It has to have both to be matter. And the reason I have these two images here with this triple beam balance with the Mountain Dew can, that would be your example of mass. And with this cube here, where we're looking at length times width times height, this would be an example of your volume. So if you can touch something, if you can interact with something, if you can feel it, any way that you can interact or touch, most likely that's going to be matter. If you can feel it, even though you can't see it sometimes, like the wind, you can't feel it, but even though the wind is very light and you think about it as not much there, it is matter. You can feel it hitting you in the face. If you wave your hand back and forth real quick right now, you can feel the wind hitting your hand. Wind is matter. Air is matter. The things that aren't matter are forms of energy. Examples of that would be light. Light would not be matter. The things that make up the light bulb are matter, but the energy that it gives off, that light energy that it gives off, is not matter. Sound is not matter. Your vocal cords, your diaphragm that helps you breathe, your lungs that help with the air to help make the sound, lets you be able to hear me right now, those things are matter, but the sound waves itself, the energy that helps or is produced with that, is not matter. And the same thing goes with a campfire. The heat that you feel off of it, or even the light given off of it, is not matter. All of those are examples of energy. Now, the first thing we're looking at with this section with matter is going to be mass. And mass is the measurement of the amount of matter in a substance or object. Now, on here, I have the SI base unit for mass is kilogram, and that is absolutely true. And I have other units here that you're going to see, like grams and milligrams. Now, both of these examples are metric. They are metric. You are used to something called English units. And this is what you're used to. These are also called customary units. English units are customary units. Examples of that could be pounds, or ounces. Those would be customary units of mass. These are your English. You're not using those. You have an idea of what those look like, how much that would weigh, or the mass of them that you would feel. But now we're moving into metric, and metric is going to be difficult because you're not used to visualizing that. You're not really too used to visualizing it, and we'll get better over time. But milligrams is going to be for really small masses. Grams would be small to medium masses, and kilograms are medium to large masses, depending on what you're measuring. And the reason I have this nutrition fact over here is you still see a serving size as 1 ounce. But it's also in metric, 30 grams. So we can see mass in there. And when you look at all of the different things, like the fats, the carbohydrates, the sodium, the sugar, they're all, right now, there's your milligrams. there's milligrams, there's grams, 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 milligrams, grams, 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 grams. All of those are measured with metric units. They're measured with the things that you're not even used to using. The only time you see anything different is right here with ounces. But everything else is measured with metric. We're going to get a little bit better at measuring with that in this section. So one of the first things here with your metric, or with mass, is mass versus weight. And this is a confusing topic at times for people, especially in science. Mass and weight are not the same thing. Mass, as we've already said, is the measurement of the amount of matter in a substance or object. Weight is a measurement of the force of gravity on an object. And you can see that down in this picture. The mass of the person is 50 kilograms on Earth and Mars. The mass is the same. Remember, mass is how much stuff. If you go to Mars right now, we did not change how much stuff you were made of. Okay? You still have the same stuff in you, so your mass wouldn't change. But the weight on Earth is 110 pounds, but your weight on Mars is 42. Your weight went down on Mars because, as you can see, Mars is smaller and it has a lower gravitational pull. It has lower gravity. So if it has lower gravity, it's not pulling you down as hard. And if that is the case, you have less weight, even though your mass didn't change. The reason it gets so confusing is on Earth, mass and weight are interchangeable because more mass equals more weight, because everything is the same. The gravity is the same everywhere on Earth. It doesn't change. So if your mass changes, your weight changes. If your weight changes, your mass changes, because it's the same everywhere. The gravitational pull is not different. But if you go to other planets or other moons, if you go to our moon, if you go to places where the gravity is less, now mass and weight are not the same thing, okay? So we have this little Venn diagram here just to help. Again, weight is the measurement of gravity. So we're looking at the measure of the force of gravity. Weight will change. It will change. The weight will change, and that's depending on the mass of an object and the strength of gravity. So if your weight goes up, if your mass goes up, or if the mass of the object you're standing on goes up, then your weight goes up. Again, Earth to Mars. As you can see, as we go from Earth over to Mars, Mars gets smaller, so the mass of Mars is less, which means that the gravitational pull is less. And you're going to measure weight in pounds. You could measure it in kilograms, depending if you're in Europe or anywhere else but the United States. And you also can measure it in a thing called newtons, and we'll get to that later this year, but that's what you can measure them in. Mass, then, mass is the amount of matter in an object. And mass will not change unless you lose or, whoops, I put loose. Unless you lose or gain, let's say, stuff. If you cut your hair, you lost stuff. So you lost mass. If you put on weight here, you put on mass. So that'll make it go up. In this class, again, we're going to be measuring this in kilograms, grams, and milligrams. With this being our English customary, and this being our metric. So measuring mass. Now when we actually measure it, you're either going to measure it in a triple beam balance or an electronic scale. In both of these, they're going to be measured in grams. You're going to measure in the unit grams, and grams is abbreviated with that lowercase g. An electronic scale is really easy. All you're going to do is turn it on, And then you're going to hit the button that says tare or 0. And then it's going to say 0.00, and you're going to put the object on there. And then it's going to give you a number, and then you're going to write it down. That's all you got to do with an electronic scale. The triple beam balance is a little different, and I'm going to have a video attached in this section to help you go over how to use the triple beam balance, okay? But these steps here are just general. Now there are different parts here when we're talking about what the triple beam balance does. Your 10-gram rider is going to be that mass that you slide up and down, or left to right, let's say, and that goes up in 10-gram increments. Your 100-gram rider does the same thing, left to right. It goes up in 100-gram increments. And your 1-gram slider is your precise slider. You can slide it the whole way, and that's what's going to finally zero everything out. Now your 100-gram rider and your 10-gram rider, you see these little notches here? They have to be in a notch. They have to be locked in. This arrow that you see, you can barely see, must be pointing directly at a number. It can't be out at all, or it'll mess up your whole measurement. When you begin using the triple beam and when you end, you want these 0 lines. These 2 lines here, bump, bump, they want to be lined up right there. And whenever you're trying to initially get it set, when we start talking about the counterweight or the counter knob, or turning the knob left to right, we're talking right here, this little knob here at the end. If you turn it one way, it moves the mass closer to the scale. If you turn it the other way, it moves it farther away. And that helps balance out the triple beam. Now comes for reading the triple beam balance. And I'm going to zoom in on just one of these at a time. When you're reading the triple beam balance, you have to add all of the masses on the beams together. So let's look at that. So we're going to zoom in again right here. The 100-gram and the 10-gram beams, they are going to just read them. They are what they are. The 1 gram is where it's going to give you a little bit of difficulty. So we see here at the 100-gram, we have 200 grams plus, here at the 10-gram, we have 30 grams. And then we're going to go look here at the 1 gram. Now the 1 gram looks very similar to a meter stick, and that's because it reads the same exact way. Only instead of this being centimeters, this is 1 gram, 2 grams, 3 grams, 4 grams, 5 grams, 6 grams, 7 grams. And then each one of these little tick marks, that would be 0.1 grams, 0.2 grams, 0.3 grams, 0.4 grams, 0.5 grams, 0.6 grams, 0.7 grams, 0.8 grams, 0.9 grams. It reads the same way as a meter stick, just now we're talking grams, we're not talking centimeters. So if we're reading it the same way, we know that it goes past that 1, this marking right here. It goes past the 1, so we have 1. Point, because now we're going down into the points here. It goes past a 0.1, it goes past a 0.2, it does not go past 0.3. So we know we have 1.2, and now we have to do our guesstimating somewhere in between here. Again, it's going to work the same way as the meter stick. If you think it's closer to the 0.2, it's going to be, the number here is going to be a little lower. If you think it's closer to the 0.3, it's going to be a little higher. If it's closer to the middle, it's going to be somewhere in between. The answer here could have been anywhere from, I would say 1.2, let's go with 2. You could have said 1.23, I would have accepted. 1.2, whoops, sorry. 1.24, even 1.25. When we zoom out here, it's harder to see. And on your triple beams that you use in class, it is going to be harder to see. Here I can zoom in, and we can see it's probably closer to right around here, I would say. It doesn't look like it's quite halfway. It's a little closer. But we would add these together now. 200 plus 30 plus 1.22 gives me an answer of 231.22 grams. If 231.23 grams, 231.24 grams, 231.25 grams. And you can have any of these. Any of these are correct. You don't need to type in the range. You just need to pick one of those, and it would be the correct answer. Any one of those. You don't need to type the range into there. So let's go back over here and we'll do another one. When we're looking at this, we have again 0. So we got 0 grams. It's all the 100 gram is all the way over to the left. Plus, we have 0 grams here. Plus, now we have to go to our 1 gram. It doesn't go past the 1, so we're starting with a decimal place. Whoop. And when we zoom in, it is easier to see. Now when we zoom out, it's not. Zoom in, it is. It looks like it doesn't quite make it to the 0.9 mark. It doesn't quite make it. So you could have had an answer of 0.89, or if zoomed out you say it made it there, I would have accepted 0.90 there. Either one of these would be correct. So our final answer when we add them together would have been 0.89 grams or 0.90 grams. Either one of those would be a correct answer. If you wrote it with the 0 out front, that is also correct. That does not make it wrong. You will get some practice with measuring mass with triple beam balances, so reading these, you will get some practice with it. If you have any questions on this, please feel free to email me. Please feel free to ask me. And remember, when we read the triple beam balances, they get read, the 1 gram. The 1 gram gets read the same way as a meter stick. Thank you, everybody, and have a wonderful day.